Welcome to today's episode. We're diving into the fascinating world of database systems and the critical importance of data integrity. As technology evolves, so do the systems that store and manage our data. We'll explore how these systems adapt through versioning, the role of checksums and error detection, and the principles of binary data organization. So, let's jump right in. Database systems are dynamic entities. They don't just sit still. They continually evolve as developers introduce new features, fix bugs, and enhance performance. This evolution often leads to changes in the binary file formats used for data storage. One of the key challenges that come with these changes is ensuring backward compatibility. Storage engines must support various serialization formats, which means they need to identify the version of any given file. For example, let's consider Apache Cassandra. It employs a clever method of versioning by using prefixes in its file names. Starting from version 4.0, data files are named with the na prefix, while older files from version 3.0 carry the ma prefix. This simple yet effective approach allows users to determine the file version without needing to open it. On the other hand, some systems, like PostgreSQL, store version information in a separate file called PG version, while others might embed the version directly in the file header. This flexibility in version identification is crucial for creating version-specific readers that can accurately interpret file contents. Now, as we rely more heavily on these database systems, the risk of data corruption due to software bugs or hardware failures becomes a significant concern. To mitigate these risks, various error detection mechanisms come into play, such as checksums and cyclic redundancy checks, often referred to as CRCs. It's worth noting that while some sources may conflate checksums, CRCs, and cryptographic hash functions, each serves a distinct purpose. Checksums provide a basic level of error detection but have limitations, especially when it comes to identifying multiple bit corruptions. They typically use simple techniques like XOR operations or summation. In contrast, CRCs are more sophisticated and can detect burst errors, those pesky multiple consecutive bit errors, by employing polynomial division and lookup tables. Given that many failures in communication networks and storage devices manifest as multi-bit errors, CRCs play a vital role in maintaining data integrity. However, it's important to clarify that neither non-cryptographic hashes nor CRCs should be used for verifying whether data has been tampered with. For that, strong cryptographic hashes are necessary, as they're designed to withstand intentional alterations. The primary goal of CRCs and checksums is to ensure that data remains unchanged due to accidental errors. When it comes to implementing checksums, the process is quite straightforward. When writing data to disk, a checksum is computed and stored alongside that data. Then, when we read the data back, the checksum is recalculated and compared to the original. If there's a mismatch, it indicates potential corruption, prompting the system to discard the data. Now, computing a checksum for an entire file can be impractical, especially if we don't read the entire file each time. This is where page checksums come into play. These are calculated for smaller segments of data, or pages, and stored in the page header. This approach enhances robustness, allowing for the detection of corruption within a single page without needing to discard the entire file. As we continue our exploration of database systems, we've touched on the organization of binary data. This involves serializing primitive data types, combining them into cells, and constructing slotted pages from these cells. Understanding how to handle variable-size data types like strings, byte sequences, and arrays is essential for effective data management. The slotted page format is particularly noteworthy. It enables referencing individual cells externally by their cell ID, maintains the insertion order of records, and preserves key order through sorted cell offsets. These principles are foundational for creating efficient binary formats for both on-disk structures and network protocols. Today we've covered a wide array of topics related to database systems, from versioning and error detection to binary data organization. As technology continues to advance, grasping these concepts becomes increasingly vital for developers and data professionals alike. By implementing robust error detection mechanisms and adhering to best practices in data organization, we can ensure the integrity and reliability of our database systems. Thank you for tuning in. We hope you found this discussion insightful. Join us next time as we explore more topics in the ever-evolving world of technology.